Hello, folks. I'm Tong from ByteDance, and it's my pleasure here to share our experiences on serving one of the largest live streaming applications with a unified architecture named AnchorNet. And as the paper title suggests, we consider two modes of live streaming. And the first one is basic live streaming, or I'll just refer to as live streaming for short, where the host of each live channel is the only broadcaster. And the second mode, which is a more interesting one, is called collaborative streaming. Multiple collaborative broadcasters can stream to a common group of viewers at the same time. And this collaborative streaming mode greatly increases our user interactivity and engagement, but of course also brings challenges to our live streaming system. So this is the roadmap of my presentation today, and I'll start with the detailed challenges. And challenge number one is that the introduction of a new streaming mode involves different protocol stacks. On one hand, we need to implement the whole WebRTC protocol suite between different collaborative broadcasters because they need to chat with each other in real time. And on the other hand, like many other service providers, we leverage HTTP-based CDN distribution to massive viewers due to its superior cost-effectiveness on the server side. And the second challenge originates from the need to mix the media streams from multiple collaborative broadcasters into a single stream watched by viewers. And where to enforce such stream mixing is perhaps the most crucial design choice for our streaming architecture. A broadcaster-side mixing can simplify server-side processing, but it increases the burden on the broadcaster device and may suffer from higher first-mile congestion. In comparison, server-side mixing has higher server-side computation overhead, and that means higher cost on server machines. And then, viewer-side mixing may require us to implement end-to-end WebRTC stream forwarding. At least at the moment, that is usually more expensive than traditional CDN distribution. Considering that we have a very large population of live streaming viewers, so we can amortize the server-side overhead and cost. And therefore, we adopt server-side mixing in our system, both for our previous architecture and for AnchorNet as proposed in this paper. But I should point out that there is actually no single best choice among the three options as I list here. And the last challenge I want to explain is the smooth splicing of media streams when switching between streaming modes, especially for audio stream. Because we adopt server-side stream mixing, we need to splice the mixed stream generated on the server side in collaborative streaming and the single stream published by the channel host broadcaster in basic live streaming mode. For video, we can simply switch to or from the mixed stream at the boundary of a K video frame. However, due to inherent encoder delay of most audio codecs, simply switching between two audio streams of different streaming modes will induce noticeable audio glitches. And as illustrated in the figure on this slide, when a channel enters collaborative streaming, the audio encoder will insert several silent samples in the beginning of the mixed stream, corresponding to its encoder delay. And that is called priming. And the number of priming samples may not be divisible by the audio frame size. And for some popular audio codecs, such as AAC and Opus, priming may generate more than one silent audio frames, and making it even more observable and noticeable by viewers. Corresponding to that, there will also be the same number of tail audio samples that are not yet included in the output audio frames in the end of collaborative streaming. That causes loss of valid audio signals. And the audio glitches induced by audio encoder delay may be more complex in a practical setup, especially when different codecs may be adopted for live and collaborative streaming. For example, in our deployment, the broadcaster uses the AAC codec in live streaming mode, but changes to Opus codec in collaborative streaming. And correspondingly, we need to transcode the Opus streams to a mixed AAC stream so that we can deliver a continuous audio stream to viewers regardless of the streaming mode. And in that process, there will be double priming induced by both codecs when entering collaborative streaming. The switching of audio codecs also causes discarded tail samples at the end of both streaming mode. And meanwhile, due to the difference in frame sizes, the Opus audio samples from the channel host probably cannot align perfectly with the transcoded AAC frames. And at last, when switching back to AAC codec, the basic live streaming mode will again start with priming silence as well. And adding those things together, the usage of different audio codecs in different streaming modes may just make the resulting audio glitches even worse. Then our design in this paper can be divided into two parts. In the first part, we evolve our streaming architecture. Our previous architecture is named as DualNet. It only supported the basic live streaming mode at first, and the end-to-end path is pretty straightforward there. The channel host publishes to CDN, and CDN is responsible for HTTP-based distribution. Then we extend to collaborative streaming several years later. And at that time, we tried not to change the existing implementation for live streaming and came up with a different end-to-end path. Since we need the RTC stack between collaborative broadcasters, the RTC MCU server publishes to CDN instead of the broadcaster. For your convenience of understanding, the RTC MCU server is responsible for compute-intensive tasks such as stream mixing and transcoding. And the RTC SFU in the figure is the edge server instance that conducts RTC media stream overlay forwarding. After years of operation, we noticed several key issues in DualNet. First, the ingestion node to CDN may change when switching between streaming modes. And second, there are two different publishing paths, one from the channel host in live streaming and another from the RTC server in collaborative streaming. Therefore, there's a high chance rebuffering may happen each time a channel enters a new streaming mode. In addition, the optimization of user experience involves many stakeholders and many internal teams at our company. That leads to implementation ossification. So when designing the AnchorNet architecture, our very first target is try to unify the end-to-end path in live and collaborative streaming. As marked in the figure, we leverage the RTC SFU server as the anchor point that ingests to CDN. By doing so, AnchorNet can guarantee the same publisher ingest to CDN. And moreover, the broadcaster uses the same media and transport protocols in both streaming modes. So there is no switchover between different streaming sessions. But meanwhile, during mode switching, RTC SFU should also splice the live streaming audio stream from the host broadcaster and the mixed collaborative audio stream from the MCU server. To address the challenge there caused by audio encoder delay and to realize smoother streaming mode switching experience, we propose various audio sample level splicing techniques. First, to avoid discarding tail samples in the end of each streaming mode, we duplicate the tail samples at the host site based on the corresponding encoder delay. Then we add extra priming samples in the start of each streaming mode to make sure the final number of priming samples can be divisible by the audio frame size. In that case, we can simply discard any audio frames containing priming samples in the output stream. That will generate smooth audio experience with no priming silence and without loss of valid audio signals as well. The figure shown here illustrates the case when we switch from live to collaborative streaming. And the two splicing techniques also apply to the other direction, of course. And due to limited time, I will just skip the details of the other two optimization techniques. Please read our paper if you are interested. Next, I'll show some representative performance gains of AnchorNet in its deployment of one of our major streaming applications. The results are from a large-scale A/B test that lasts 4 weeks in Q4 of 2024. It involves tens of millions of users each day, as shown here. And the first part, AnchorNet significantly reduces audio and video rebuffering. And as exemplified in this figure, in the case of switching from live to collaborative streaming, video rebuffering duration is reduced by 60%. And on the other direction, when switching from collaborative streaming back to live streaming, video rebuffering is reduced by nearly 80%. And of course, in our paper, you can find similarly large reductions for audio rebuffering. And such a smoother experience when switching between streaming modes naturally increases our user satisfaction. And that is reflected by increased engagement from all rows of our users. For example, this is a trend of streaming duration of collaborative broadcasters in collaborative streaming modes during the test. AnchorNet consistently outperformed DualNet with an average performance gain of 2%. And the viewer watching duration is also increased by nearly 4%. That validates the effectiveness of AnchorNet in practice. At last, I also want to briefly mention some possible future optimizations that may be needed for AnchorNet. First, the end-to-end streaming latency in AnchorNet still has room for further reduction. And that is because the RTC MCU servers used to conduct stream mixing and transcoding are currently mostly centrally deployed. We're interested to increase edge deployment for those compute server instances, but that will require careful resource provisioning and scheduling for server-side cost control. And second, one thing we're actively working on right now is the co-optimization of stream mixing in collaborative streaming and transcoding for other purposes, such as ABR. And that requires close coordination with our CDN providers. Okay, so that is all for my presentation. I'd be glad to take questions. Thank you.